We are now going to investigate the effect of current on the strength of the magnetic field. So here you can see we have our solenoid set up, and it is connected to a power supply. And we have a multimeter here to allow us to measure the current. So we're going to be changing the current with this knob here. And you can see the current adjust on this screen here. We'll be going by increments of 50 milliamps. So I'll set it, maybe you can see it on the video here, I set it at 50 milliamps, then I'll set it at 100 milliamps, and we'll keep increasing the current. And we'll be looking at the deflection of the needle on the compass. And you can see that the compass is placed at this distance 10 centimeters away from the front of the solenoid coil. So we will keep the magnet in place the entire time, and we will be taking a look at how the deflection of this compass needle changes. So I'm going to zoom in on this compass needle so you can see it, and I will be reading off the current values as I change them. So you won't see the multimeter. I'll tell you what those values are, but you're going to be looking at the compass. You'll pause the video probably in order to be able to best see what the angle is and take that measurement. So let me move the camera. Okay, we're looking at the magnet here a little bit more closely in order to be able to see the deflection of the compass needle. In fact, I'm going to zoom in even a bit more so that you can really read these angles. So you can see that the arrow is pointed at 0 degrees. And so when I increase the current to 50 milliamps, click that on first. So I increase to 50 milliamps. I'll let you know when I arrive. All right, so we're at 50 milliamps. You can see the deflection of the needle has changed to, it's a little bit past 10, it's a little bit under 20, and the scale is going to be going by 2, so this looks to be at about 14 degrees. So that's how we can take our measurements here. So at each of these currents, I will tell you when I reach the current, and I'll say that you can pause and take your measurement, and then you can unpause and continue the video. So we're also going to be reversing the polarity of the current going through the solenoid. So I'm going to unplug these wires, and you'll see that the needle reverses direction because now the field is pointing in the opposite direction. So you can pause here, take your measurement. All right, and now we'll continue on. And for ease of doing this, I'm going to keep it in this reversed polarity as I go up to 100 milliamps. So you're going to take then that measurement here in this reversed polarity. So keep that in mind as you are recording these results and then entering them on the Excel spreadsheet. That we're going to be kind of going back and forth. It's going to be forward, backward, backward, forward, forward, backward, backward, forward. It'll be important to keep those in mind. Okay, so you can pause here, take the measurement at 100 milliamps. Okay, now I will swap. Okay, you can pause, take the measurement. Now we'll go to 150 milliamps. So I have to take some time to adjust. It's a fine adjustment. All right, so that's 150. You can pause. Okay, now reverse polarity. All right, settled. You can pause. All right, now we go to 200. All right, there we go. 200 milliamps. Pause. And reversing back to the original forward direction. Okay, you can pause. Now we go to 250 milliamps. This will find me. Okay, 250, pause. Now I reverse. All right. So this is 250 milliamps reversed polarity. You can pause. Now I will go to 300. All right, 300 milliamps, reverse polarity. Pause. And I will now go back to forward polarity. Okay, it's settled. So that's 300 milliamps forward polarity. All right, now I go to 350. Okay, I'm at 350 milliamps forward polarity. Pause. And reversing polarity. 350 milliamps. Okay, pause. So 400 to 400 we go. This really isn't that much more exciting in person either. So the fact that you're watching it on video, anyway, 400 milliamps in reverse polarity. You can pause. Okay, now we go back to forward polarity. All right, you can pause. Upward towards 450. $450 milliamps. Pause. All right, now reverse polarity. 450 milliamps, reverse polarity. Pause. One more to go. Let's go to 500. 500 milliamps. There we are, 500 milliamps. Reverse polarity, pause. And one last switch back to forward polarity. Let the needle swing. And you can pause 500 milliamps. Okay, that's it. Let's drop it back to 0. Let's hope it goes back to 0 itself. That'll be encouraging. Yep, pretty good. Okay, there you go. It's time to get these numbers into Excel and start making some graphs. One of your pre-lab questions was to think about how the direction of the magnetic field of the Earth and the direction of the magnetic field of the solenoid relate to each other, so that we can actually determine what is the ratio of one field to the other, so we can actually say something about the strength of the magnetic field. So we have this set up such that with no current running through the solenoid, the compass is going to be, the north is going to be pointing, let's say, upward. So that is the direction of the magnetic field of the Earth. So if I want to draw a vector for that, B for the Earth. Then we run a current through the solenoid. So say we send a current through this wire here, and the current comes out over here. So depending on the direction we have this going, if we can use the right-hand rule and have the current as coming up along the back and then running forward, the right-hand rule says that the magnetic field lines are going to be coming out and pointing to the right through the solenoid. So now that is going to cause the compass needle to deflect. So the compass will now, say, be deflected this way. Now let's say it's a fairly strong field, so that we have a fairly large deflection. So we would want to figure out, well, what is the angle at which this is deflected? So this is going to show us what our net vector is between the magnetic field of the Earth and the magnetic field of the solenoid. So now we see we have some net vector, which must be at least this high vector-wise. Some net vector which points that way. So if we resolve that and find the x component, this x component is actually telling us what the magnetic field of the solenoid is. So it'd be solenoid. So given that we can measure the angle here, if we know that this upward is at some, let's say it's 0 degrees, and then we find that this deflection is, let's say, I don't know, let's make up some number, let's say 70 degrees. So we can say this is 70 here, and if we want it, we could say that this is 30 degrees there. So we could take a look at this ratio. We could see that, assuming that we know this to be 30, or, well, actually, I think 70 is the one we're actually interested in. So if we look at this, we can see that this length here, this height, is the solenoid divided by B earth. That is going to be the tangent of this 70. So B solenoid over B earth is equal to the tangent of 70 degrees, or generally the tangent of the angle. So when we find this angle, we just need to take the tangent of that value, and we find this ratio.